Okay, section 5.4. Okay, is on the comparison tests. Okay, so the comparison test okay, the first one we're going to talk about, suppose that you have two series, series A sub n and series B sub n, okay, are series with positive terms. Okay, one. If B sub n, the series with series B sub n, is convergent, and the B sub n terms are always greater than or equal to the A sub n terms for all n, then the A sub n series is also convergent. Okay, so if A sub n is less than a known convergent series, then A sub n must also converge. Okay, a diagram showing that would be that if I have my A sub n, my series B sub n converging to something, so say that, okay, B sub n converges, okay, and these terms are always smaller, okay, I'm adding smaller values each time, okay, with A sub n, then A sub n must also converge. They may not converge to the same thing, but it must converge. If this is B sub n and this is A sub n, then it's bounded. If B sub n is bounded and A sub n is always, those terms are always smaller, then B sub n then A sub n is also bounded. Okay. Okay, number two, the converse is true, or we should say the contrapositive is true. Okay, if A sub n is divergent, okay, and once again, B sub n is greater than or equal to A sub n for all n, okay, then the sum, then the B sub n series is also divergent. Okay, so let's do a picture on this one. So if A sub n is divergent, okay, so the terms just go to infinity. Okay, A sub n, the partial sums go to infinity. And B sub n is always bigger than that, is always bigger than A sub n. The terms are always bigger. Then the series B sub n must also go to infinity. Okay, it also must diverge. Okay, let's do an example with this. Determine consider this series summation n equals 1 to infinity excuse me, of 5 over 2n squared plus 4n plus 3 converges or diverges. Okay, so let's find something to compare this to where the terms are going in the right direction. Okay, so we have this kind of series where we say, you know, this guy we could compare with n equals 1 to infinity of 5 over 2n squared. Let's just compare it with that guy without all the extra stuff in the denominator. Okay. Okay, how does that help me? Well, this thing is a p-series. This thing is a convergent p-series. Okay, it just has the 5 halves in front, which is fine, but it's still a p-series. This converges for p-series p equals 2, which is greater than 1, so it very much converges. Okay, since we could have just pulled that 5 halves outside and gone 1 over n squared. So that definitely is a p-series. It converges. Okay, due to the p-series. Okay, now I have to kind of compare the terms, and we need to say, okay, which one is bigger and which one's smaller? Which one's a sub n and which one's b sub n? Because again, if this is bounded, okay, if this is bounded by something that's bigger, then we're good. Okay, so let's compare 5 over 2n squared plus 4n plus 3, okay, and 5 over 2n squared. Okay, let's compare these. What is the net result of adding these extra terms on the bottom? Does this make that my value bigger or smaller? If I add extra stuff, keeping in mind that n is always positive, if I add extra stuff to the denominator, that's actually going to make the value of the function by dividing by more stuff is going to make it smaller. Okay, thank you, Jose. Okay, yeah, absolutely. So this is going to say that 5 over 2n squared plus 4n plus 3 is less than or equal to 5 over 2n squared. And I know that the series n equals 1 to infinity of 5 over 2n squared plus 4n plus 3, okay, that is now bounded by a convergent series. This thing converges 5 over 2n squared. This converges. Okay, and since this is always less, okay, the sum of the terms are always less than a known convergent series, okay, it will converge by the comparison test. So therefore, since n equals 1 to infinity of 5 over 2n squared converges, the summation n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 also converges by the comparison test. Okay, so that converges. Okay, what if the inequality went the wrong way? Well, mathematicians came up with a kind of an ingenious way of dealing with that. Okay, say we instead of up here we were adding these terms. What happens if we were subtracting those terms? Well, then we couldn't use the we couldn't use the comparison test, but we could do something else. And that's called the limit comparison test. Okay, so let's talk about the limit comparison test. Okay, this is if we have this comparison of series set up, but the inequality goes the wrong way. And, you know, the algebra doesn't work out as nicely. So then what do we do? Okay, suppose that the sum of a sub n and the sum of all the b sub n's, the series a sub n and series b sub n are series. Okay, with positive terms. Okay, if the limit as n goes to infinity of a sub n over b sub n is equal to c, okay, where c is a constant, if this limit of the a sub n over b sub n is equal to a constant, okay, actually a positive constant where c greater than 0 is a positive constant, then the series plural, okay, either both converge or both diverge. Okay. Okay. Okay, let's do an example with this. Okay, example number 2. Okay, so test the series summation n equals 1 to infinity of 1 over 2 to the n minus 1, and this is a minus 1 on the bottom, for convergence. Okay, so it's 2 to the n minus 1, not just the n minus 1. Okay, it's the whole thing minus 1 for convergence. Okay, let's compare with our known series n equals 1 to infinity of 1 over 2 to the n. Okay, which can be written like this, n equals 1 to infinity of 1/2 to the nth power, which is a known converging geometric series. Okay, this is a convergent geometric series with r equaling 1/2. Okay, the common ratio is 1/2 here. Okay, and since 1/2 is less than 1, it converges. Okay, so that's convergent. The only problem is that when I compare these two, let's say that a sub n is equal to 1 over 2 to the n minus 1, and b sub n is equal to 1 over 2 to the n, the only problem is that the inequality goes the wrong way. Okay, this thing is actually bigger. Okay, this R series is actually bigger than the convergent series that we want to compare to. So the inequality goes the wrong way. So the inequality goes the wrong way for the comparison test. So we use instead the limit comparison test. Okay, so let's take the limit, okay, as n goes to infinity, of a sub n over b sub n, and see what this gives me. So this is going to be 1 over 2 to the n minus 1 all over 1 over 2 to the n. Actually, there's a limit there. Let's plug in the limit. Okay, this is going to be equal to 2 to the nth over 2 to the nth minus 1. Again, there's a limit there. I don't know why I keep skipping the limit. Limit as n goes to infinity of 2 to the nth power over 2 to the n minus 1. If we divide both top and bottom by 2 to the n, we get the limit as n goes to infinity of 1 over 1 minus 1 over 2 to the n. This goes to 0, so this thing equals 1. Okay, which is a constant. It's a positive constant, which is my c. Okay, since it is a positive constant, I know that both of my series either both diverged or they both converged. So they're both series converge or both diverge. And since we're comparing against a known convergent series, since n equals 1 to infinity of 1 over 2 to the n converges by the limit, or I'll just say so does the series that we're looking at, which is n equals 1 to infinity of 1 over 2 to the n minus 1. Okay. Okay, therefore, n equals 1 to infinity of 1 over 2 to the n minus 1 converges by the limit comparison test. Okay, let's do one last one here. Okay, number 3. Test the series summation as n equals 1 to infinity of natural log of n over n for convergence. Okay, and I'm going to use just the comparison test, the basic comparison test. Sometimes it's called the basic comparison test. People want a qualifier, as limit is comparison test and basic comparison test. You could call it the basic comparison test if you want. Okay, it's just the comparison test. Okay, I'm going to use just the basic comparison test here. Okay, and we're going to compare this, okay, with the harmonic. Okay, compare with the harmonic here. Well, I can compare the terms, but I can't start at 1 because the inequality goes backwards for the first few terms here, but then it eventually, this guy, natural log n, will start getting bigger and bigger than 1 over n. So let's look at that. If I take the series n equals 1 to infinity of natural log n over n, what do the terms look like? Well, they look like natural log 1 over 1 plus natural log 2 over 2 plus natural log 3 over 3 plus natural log 4 over 4 plus, and kind of goes on forever. Okay, natural log 1 over 1 is 0. Natural log 2 over 2 is 0.693. Okay, that goes on forever, over 2. Natural log of 3 is where we get 1.099 over 3. Natural log of 4 is 1.609 over 4. Okay, and then kind of goes on from there. And we're comparing this against the harmonic series. And we're saying, okay, well, this is 1 over n. So this is 1 over 1. Okay, plus this is going to be 1 over 2 plus 1 over 3 plus 1 over 4 plus ... And notice that these terms are smaller, but then eventually the numerators go bigger, okay, than 1. These terms are smaller, so what we're going to do is we're going to kind of cheat. We're not going to use the first 2 terms here. We're going to actually wait until we get to something bigger. We don't really care if something converges or something diverges. It really doesn't matter what the first couple terms are doing. It's either going to converge or diverge. Okay, we could chop off the first 2 terms. That's fine. Okay, and so now if we restart these with n equals 3, natural log of n over n, and n equals 3 for 1 over n, then we know that this thing diverges. And we now know that 1 over n is greater than or equal to natural log of n over, sorry, that's the other way, my bad. Okay, 1 over n is less than or equal to, okay, natural log of n over n for n greater than or equal to 3. Okay, so we have to start at 3. Okay, and since this is bigger than a known divergent, remember, if 1 over n diverges, okay, but natural log of n over n is always bigger than a divergent sequence. The thing here is, though, we're starting at, instead of 1, we're starting at 3. Okay, and we're saying that these things are always, okay, divergent. okay, then it's going to be divergent. Okay, so this thing diverges. So therefore, since summation n equals 3 to infinity, this should have an infinity, okay, of 1 over n diverges. Okay, we could call it the harmonic, or we could say P series, P equals 1. Either way, we know that this diverges for everything from 3 or more. And B sub n is always less than A sub n here. Then we know that n equals 3 to infinity of natural log n over n diverges. And thus, adding back those two terms that we took off doesn't make it diverge any less. Thus, n equals 1, I can back in those couple terms that we took off. Natural log of n over n also diverges. Okay, and this is proven by the comparison test. Okay, so this thing is divergent. Okay, and that is okay, that is 5.4.